All right, we are back. I apologize for the audio issues that we had in the last video. This is what happens when you try and mess with your audio and try and stream League of Legends competitions, but you know how it is, right? All right, so let's talk about piecewise functions. We're on day 2. We're over here on day 2 in the packet, which, whoops, we didn't put page numbers on for you, so we'll, day 2, find day 2. Transformation of the absolute value function is written here as a piecewise function, so we're going to deal with absolute value again to start this discussion of the piecewise functions. So don't forget that this is the rule, these are the rules, and this tells us when to use each rule. So here's how we're going to graph a piecewise function. We're going to make a table for each piece of the piecewise function. So in this case, there are 2 pieces. Okay, right? So it's like the number of horizontal lines. So for the first piece, right, I can have my x values, and I can have my values for the first rule, right? So negative x plus 3. Okay, now what x values am I going to be using? I'm only going to be using x values that are less than 3. I am going to put the 3 in the table, but I'm going to make a note that I'm not going to include it. So if x is less than 3, I'm going to start with the 3, and then I'm going to go less than that, right? So 3, and then 2, 1, 0, and so on, right? That will go on forever. Now, for the output, I just plug 3 into the correct rule, right? So we're talking about the first rule here. So plugging 3 in for this, it would be negative 3 plus 3, which is 0. Right? Negative 2, now take the 2, plug it in. Negative 2 plus 3 is 1. Negative 1 plus 3 is 2. Negative 0 plus 3 is 3. And that will go on forever. Okay, and so I use those dots. I will maybe even include like an arrow type thing to make sure I know that when I go to graph that, I'm going to use an arrow on this side of the graph. I'm also going to make a note that this point right here is not going to be included when I graph this piece. So I'm going to circle it because I'm going to graph this as an open circle. So I do have to graph the point 30, but because it's not included on this piece of the function, I graph it as an open circle. Now I have to create the table for the next rule, which is x minus 3. And this is for x being greater than or equal to 3. So I'm going to start with 3. I'm going to go greater. So 3, 4, 5, 6, and so on. It goes on forever. And I'm going to plug this in. So 3 minus 3 is 0. 4 minus 3 is 1. 5 minus 3 is 2. And so on. That goes on forever. Okay? Now we can start to graph this. So I'll just start graphing these. So if I look at the first table I make, I'm going to graph this at 3, 0, 1, 2, 3, 0, and I'm going to graph it with an open circle. I'm not going to fill it in. Okay? And then 2, 1, and then 1, 2, and 0, 3, and then it goes on forever. And so in this pattern that I'm doing, I can just continue that pattern, or I can just do this and show that it goes on forever. So that's why I put an arrow there to show that in that direction it goes on forever, and I put the arrow because I have to remember to put the arrow there. Next one, I'm going to just graph this table now. So 3, 0. So I go to 3, 0, and here I am at this same point. So I'm going to actually go ahead and fill this in now. because I'm able to, right? Because now this point is included. So now I continue 4, 1, 5, 2, 6, 3, and this goes on forever. So I can continue this pattern forever and draw my arrow. And that, I just graphed a piecewise function. It looks like an absolute value function because it is. Okay? A piecewise function is simply a function that is broken into pieces. And so because it's broken into pieces, we're going to create a table for every single piece. Sometimes the pieces will line up and connect like they just did in this first example. Sometimes they won't. Sometimes there'll be gaps in the graph. Okay? Because we can pretty much make a piecewise function however we want. It just has to still follow those same ideas to make it a function, which, if we remember, every function in any function, it's a relationship in which every input has exactly one output. So we can't have repeated x values, right? So that's why in this one, with this x of 3, I can't include it over here because it's already included over here. And I can't have repeated x values. So that's why one of them is open circle. The other one is a closed, filled-in circle. So we are going to make a table. These are the steps to graphing. Make a table for each piece. And then plot the points. Right, so first piece, first table is negative 3x minus 3. And this is going to be for x is less than or equal to negative 2. So negative 2, negative 3, negative 4, negative 5, and so on. Arrow. Plug this in. So we can use our calculator if we want. Plug that in, look at the table, copy down what we see in the table in the calculator. Okay, so this would be 6 minus 3, and then 9 minus 3, 12 minus 3, and so on. Next table would be 0.5x plus 4. And that's going to be from negative 2 to 2. So I'm not going to go on forever. I'm not going to have arrows in this piece of the function. I'm only going to go from negative 2 to 2. And I'm not even going to include negative 2 or 2. I'm going to have to write them on the table, but I'm going to have to identify that those will be open circles. So negative 2, and I have to work my way to 2. So negative 2, negative 1, 0, 1, and 2. And that's where I'm going to stop. I'm not going to put any arrows anywhere. Plug these values in. So again, you can just use your calculator to figure this stuff out. This would be negative 1 plus 4. So that would be 3. And then this would be 3.5 and 4, 4.5, 5. It's nice when it's a linear slope and I can just kind of go with the pattern. And I'm going to identify that this is not actually included, right? That's going to be an open circle. And this one's not actually going to be included. That's also going to be an open circle when I go to graph. Now the third piece, I'm running out of room, negative 2x plus 9. And that's when x is greater than or equal to 2. So 2, 3, 4, 5, and so on. And if I plug these in, that's negative 4 plus 9, 5, and then 3, and then 1, and then negative 1, and so on. Okay, so now we have the tables made. Now we can go ahead and graph all the tables. So negative 2, positive 3, negative 3, 6, negative 4, 9, negative 5, 12, and this goes on forever. I have an arrow at the end of that table. Next piece, negative 2, 3. So there is already a point there. And I'm going to go and plot this with an open circle. So the idea here is that we're getting really, really close to this point, and we don't actually have to replot this point, right? Sometimes I could put an open circle around it, right, to show that I've plotted this point. But that's not really necessary. We don't have to do that. I can just go to the next point of negative 1 and 3.5, right, which would be somewhere around here, and 0, 4, and 1, 4.5, and 2, 5. Now here I'm going to, because there's no point there, I am going to put the open circle here. Okay, and I'm going to go ahead and connect. Now I go to the next table, 2, 5. Okay, so now I can go ahead and fill this in. Okay, so I get this huge point. And then 3, 3. So that's going to be here. And 4, 1. 5, negative 1. And this goes on forever in that pattern. And that's an arrow as I fill it in. Okay. And so we get this kind of strange looking graph, but does it pass the vertical line test? Yes, it does. It's a function. Notice at these points even here, where we had two things, it passes the vertical line test because it only goes through the function once, because these are open circles. So, graph the function below. F of x equals the absolute value of x when x is from negative 3 to 1, and 4 when x goes from 1 to 8. Let's take a look at this one. So we have two pieces here, so we're going to make two tables. So x and absolute value of x. And we're going from negative 3 to 1. And I'm noticing that I'm not going to include 1 in this. So negative 3, negative 2, negative 1, 0, 1. I'm going to write it, but I'm going to circle it to make sure I do an open circle. And now plug x in. So what's the absolute value of x? What's the absolute value of negative 3? Positive 3, positive 2, positive 1, 0, positive 1. And this one is not included. So I'm going to put an open circle on that. No arrows or anything, right? I'm not going off to infinities. I'm just going from negative 3 to 2. So there's my table done for that. Next table. This is an interesting table to make because the function's just 4. So it doesn't even matter what the x value is, right? I'm going from 1 to 8. 1, 2, 3, 4, 5, 6, 7, 8. But there's nothing to plug in, right? If I plug x into this function, I can't plug it in anywhere, and I get 4. Can't plug 2 anywhere in, and I get 4. And I get 4 and 4 and 4 and 4. This is just a line going across at 4. Okay? So I will go ahead and continue that because I love writing 4s. Negative 3. Now I'm going to go ahead and plot this first piece. So negative 3, 3. So negative 3, 3. Right there. Negative 2, 2. Negative 1, 1. 0, 0. And 1, 1 with an open circle. So now I'm going to go ahead and try that. I just go right up to that open circle. Okay. Let me fix that. Okay. Next, 1, 4. 1, 4. 2, 4. 3, 4, everything 4 until you get all the way up to x equals 8. So 1, 2, 3, 4, 5, 6, 7, 8. Right? And all of these are 4s. And you just get this horizontal line, which hopefully comes out a lot better than that. Here's our function. Is this a function? Does this pass a vertical line test? Yes, it does. Even at x equals 1. Because that's an open circle, it's not passing through the function there. It's only passing through the function here. Okay? So this is an example of a piecewise function where it doesn't connect. It doesn't match up. Okay? So this stays as an open circle. The rest is just all plotted. Okay. That's graphing piecewise functions. What we're going to do now is we're going to take a look at a graph, and we're going to be able to write the function. We're going to be sticking with linear piecewise. So we're going to be writing linear functions, essentially. And what do we need to write a linear function? We need to know two things. We need to know the slope and y-intercept. So that's what this is doing, okay? It has broken this piecewise function up, which, by the way, it increases from A to B, it stays constant from B to C, it's just a flat line, and then from C to D, it starts to decrease a little bit. So what we're going to do is we're going to calculate the slope of each of the lines, right? So we can do change in y over change in x. We can look graphically at the rise over run, whatever's more convenient. In this case, it looks like this is 1, 2, 3, 4, 5, 6, up 6 and over 4. So 6 divided by 4, which would come out to be 3 halves. Okay, so the slope there is up 3, right 2. Follows that pattern, up 3, right 2, up 3, right 2. Okay? Remember to go from the first point to the last point, okay? Because, like, yeah, it looks like it goes through that point, but we're not entirely sure. Like, in a different setting, in a different scale or something, maybe it comes really, really close to that, and we're just not really sure. So go from the start point to the end point to figure out your slope. Here, what's the slope of a horizontal line? Slope is 0. From C to D, this goes down 1, 2, and over 1, 2, 3, 4. So negative 2 divided by 4 would be negative 1 half. Next part is to identify the y-intercept. So now that we have the slope, we know the pattern of this line. So now for this segment AB, since we know we go up 3, right 2, we know that if we were to continue that pattern of going up 3, right 2, we would end up with a y-intercept right there. A y-intercept of 1, 2, 3, 4, 5, 6. Okay, so that's what we're going to do. We're going to kind of extend these. If they're, so BC, it has a y-intercept. So this one I can just identify as 3. If it doesn't have a y-intercept because it's only right here, we have to extend that pattern, right, back toward the y-axis so that we find the y-intercept. So this is 1, 2, 3, 4. Looks like a y-intercept of 4. So putting this stuff together, segment AB we can now create a linear function, right? A slope of 3 halves and a y-intercept of 6. What would that linear function look like? 3 halves x plus 6, right? Mx plus b. Segment BC, we can write a linear function from this. If it's a slope of 0, 0x, but do I have to write the 0x? I don't really have to write that 0x, right? This would just become 3. And then segment CD, negative 1 half is my slope. So negative 1 half x plus 4. So there's the rules. Now to write the piecewise function, I'm going to do my function notation, f of x equals, and I'm going to do these little fancy squiggly brackets. And I'm going to start with the rules. So this is 3/2 x plus 6. And when do I use this rule of 3/2 x plus 6? I have to put that over here. And so if I look back at my graph, what were the x values? This x value is 1, 2, 3, 4, 5, negative 6. Okay, so negative 6. And is that an open circle or is it closed? It's a closed circle. It's included. So I can say less than or equal to. And we're talking about x values. And then I go to the endpoint. And what is my x value here? 2, negative 2. Can I include this point? Yes, I can, because it's a closed circle. So negative 2. Okay. Now I do the next rule. The next rule was 3. And when do I use that rule? Okay, so let's go to the starting point, b. That's when x is negative 2. The question is, can I include that negative 2? Remembering that this has to be a function. I cannot include negative 2 because I already included it on the last piece. So because I already included it on the last piece, on this next piece, I will not include it. So I won't put the equal sign. Okay, and then I can go down to here, which is positive 2. Can I include that one? Yeah, I can, because I haven't included it yet. So the way I like to approach these values is I go from left to right, and if I can include it, I do. Okay? And I just make sure that I don't double include anything. So the next rule would be negative 1/2 x plus 4. And when am I using that? It's from 2 to 3, 4, 5, 6. So from 2 to 6. So from 2, can I include this 2? I just included it on the last piece, so I'm not going to be able to include it here. To 6, can I include that 6? Yes, because it's filled in. It's not an open circle. It's not an arrow to infinity, right? And I haven't included it before. And so this is our piecewise function. We've just created a piecewise function based off of the graph. Okay? So obviously when we take a look at just a graph, it won't have all of this extra stuff with it, right? So here's an example of that. Here's a graph. We want to write the piecewise function. So I'm going to start with my notation here. And I'm going to make my squiggly brackets, and I'm going to leave myself a lot of room because how many pieces do I have here? 1, 2, 3, 4. I got to fit 4 different rules and domains in for this. So here's how this is how I approach these piecewise functions. What I'm going to do is I'm going to break this graph up into its separate pieces. And if you don't like to get the graph all messy, then you might not like this method. Whatever works for you, okay? If you don't want to do this, fine. But what I like to do is I like to kind of break this up to figure out what is this x value. That's negative 7. And I break it up, right, all the way here. Everywhere I go, I'm going to break up this piecewise function wherever there's a sort of like turning point, wherever it's naturally broken. And I'm going to identify what these x values are because I'm going to use those later. So this would be negative 3. This is an x value of 1. This is an x value of 4. And this is an x value of 7. Okay? Now I can easily see the domain piece, the when to use which rule piece. I can easily see that this rule is being used from negative 7 to negative 3. This rule is being used from negative 3 to 1, from 1 to 4, from 4 to 7, right? That's why I break it up like that. But you can also see that it kind of gets the graph all messy, so if you don't want to do that, fine. Now I'm going to write the linear equations. To do that, I'm going to find the slope, to right 4. So that's 1/2, right? So 1/2 x. And I'm going to continue that slope. And it looks like I have a y-intercept of 1/2. So 1/2 x plus 1/2. And that's from -7 to -3. So I've included both of those. Why have I included both of those? I don't see an open circle. I don't see arrows. And I've never used them before. So I'm good to go to include both of them. Okay? Next one is a horizontal line at what y value? -2. So it's just -2. And when do I use that rule? From -3 to 1. So from -3, and can I include -3? Hopefully you said no, because we've already included it. Can I use 1? Can I include 1? Yes, because I haven't used that before. Okay, and this is just how I do it, right? I go from left to right, figure out the slope y-intercept, write the domain. So for here, the next piece, the third piece of this, looks like up 3, right 3. So that's a slope of 1. So 1x or just x. And if I continue this pattern to the y-intercept, looks like it would have a y-intercept of -3. So x minus 3. And what's the domain piece of this? 1 to 4. 1, already used it, to 4. Next piece, my slope is going down 1, 2, 3, right 3, so it's -3 divided by 3, -1. So -1x or just -x. And if I continue this pattern, looks like I have a y-intercept of 5. So plus 5. And that's from 4 to 7. So 4, can I include that? No. Can I include the 7? Yes. Okay? That's how I go ahead and write piecewise functions. So, awesome. Step functions. So here's, again, another example of a piecewise function. In this one, there's no variable, right? It's just 3 different values. -1 whenever x is less than or equal to 0. So let's go ahead and make the table. So x, and then -1 is my output everywhere. Going less than 0, I have to put the 0 down, and then -1, -2, -3, forever. Okay? But all the outputs are -1. Right? It's just a horizontal line at -1. But what about this x is less than 0? I'm not including it. That's got to be an open circle. Okay? The next one is just a point. It's just one single point, right? Because it's only when x is 0 do we output 0. Okay, so when x is 0, we output 0. The only point for that. And then the third one is 1. It outputs 1 all the time whenever x is greater than 0. Again, I'm going to start with 0, 1, 2, 3, 4, so on, forever. But we output 1 everywhere. This is not included in that table, so I have to put an open circle. So now I'm going to go ahead and graph this. So 0, -1, 0, -1 is an open circle. Yeah, let's just go ahead and do that. And then -1, -1, right? So this point and that point forever, and it's just that horizontal line. The point 0, 0 goes right there, and then 0, 1 is plotted with an open circle. So again, we see that that still passes the vertical line test because there's only one filled in point at that 0. And this goes on forever here. And we get this function, okay? So these are examples of step functions. here's a really good step function to show why we call it a step function. So let's go ahead and graph these. So we can make our table, right? But again, these step functions don't really have variables. They're just horizontal lines, right? So this is a horizontal line at a value of 1 from -5 to 2. So I can pretty much do that, right? I can go to -5, 1, 2, 3, 4, 5, and go to 1. And since I'm including -5, I can just close that circle in there and go to -2 and put an open circle because I'm not including it, right? And it's everything between. Let's try that again. Okay. The next one is at a value of 2 from -2 to +3. But I'm not including +3. So we get something like that. And then 3, 3 all the way to 5, and we are including that. And that's the whole function there. So why do you think we call that a step function? Because it kind of looks like steps, right? Kind of looks like steps. Right, but without the vertical lines in there. It just looks like this. And we could certainly imagine some guy walking up those steps. Okay. Next, some practice. Let's practice writing a piecewise function. So I would probably have you guys pause the video here. See if you can do what I did back here on question 2, where I kind of broke the function up, figured out the rule for each piece, the domain for each piece, and wrote the whole piecewise function, okay? So that would be trying to do that on this piece. Noticing that this right here is an open circle. That's a closed filled in circle included. This is closed included. And this is open not included, okay? And then these also, I should point out, are arrows. They are very small, but they are indeed arrows there. So go ahead and try and write that function. I will continue writing mine as well. So if I'm going to break this up, that doesn't break up. That goes to negative infinity x value. Okay, but then there is a break here at what seems to be -2, and a break here at 2, and then we go to infinity again. Okay, so what's the rule for this piece? 1, 2, 3. That's just a horizontal line at -3. And negative infinity, going left to right, negative infinity to -2. Can I include negative infinity? You can never include negative infinity because you can't get there. To -2, can I include -2? Not on this piece because it was an open circle. Next piece. Okay, what's the slope? Looks like we're up 4, right 4, so that's a slope of 1. So x, y-intercept of 0, x plus 0, or just x. And we're going from -2 to 2, and both of these are closed circles, so I'll include both of those endpoints. So -2 included to 2 included. Next piece, 2, 3, 4 is a value of 4, and that goes from 2 Again, I can't include it because it's an open circle. And it goes to infinity, which cannot be included because we cannot get there. And so that's our piecewise function there. All right, moving on to question 6. Don't mind that cut there. That's nothing. Nothing's changed. Everything's the same. Nothing has changed at all. So number 6. Okay, well, that's happening. Still nothing has changed. We're still good. Okay. Still on track here for number 6. Mateo's walking to school. It's a nice morning, so he's moving at a comfortable pace. After walking for 9 minutes, he's 6 blocks from home. He stops to answer a text on his phone from his mother. After 5 minutes standing still, he walks home quickly in 6 minutes to get a paper he forgot for school. So we're going to model Mateo's distance from home D in blocks as a function of time t, which is measured in minutes since he left. So first thing we're going to do is we're going to draw the graph, right? So he's starting at home, right? So we're going to plot that little point right there, and 0, 0. And we know that 9 minutes, he's 6 blocks from home. So in 9 minutes, it takes basically 9 minutes for him to walk the 6 blocks. So we go over to 9 minutes, and now he's 6 blocks away. And we're going to connect those because he's walking at a constant rate. But then, of course, he gets the text message from his mom, which sends him into shock because he stands still for 5 whole minutes contemplating what to do. So from here, we're going to go 1, 2, 3, 4, 5 full minutes of standing still, doing nothing, just staring off into the sky, thinking about the text message, I guess. Apparently he was told he forgot something, and it took him 5 minutes to decide to go home and get it. So he walks home quickly this time, so it only takes him 6 minutes, because he spent 5 minutes thinking about it, being like, oh, I should probably hurry up now, because I've just wasted 5 minutes. So in 6 minutes, he's going to go all the way back home. So that means from here, we're going to go 1, 2, 3, 4, 5, 6 minutes, and he is all the way back home, and so that distance should be 0. And then we're going to connect those, and hopefully you hit that and didn't miss it like me. So there we go. There's our graph. Determine a formula for this graph. So we're basically going to do what we just did in question 5, because we literally just did that. It's not like anything changed in between 5 and 6. So here we go. We're going to break this up. I see that this is at 0. I see this is a break here at 9. Here's a break at 14. And then the ending here at 20. All right. So, oh, okay. Never mind. Sorry. This is breaking this down into each piece, right? So I've already jumped to part E. I was ready to do part E. This is actually just breaking it into all the different pieces. So again, this is like a step-by-step type thing. So for the first piece from 0 to 9, what's the linear equation essentially? Well, we have a y-intercept of 0 and a slope. It's going up 6 over 9. And so that would be something like this, right? Which we know could reduce to 2/3 x, and we wouldn't have to put the plus 0. And then for the middle piece, that's a horizontal line. So it's a horizontal line at which value? It's a value of 6. So the rule would just be d equals 6. And then for the last part is going to be this part. So we can figure out the slope we are going down 6 and right 5. There's the slope, but we don't know what the y-intercept is. So I'm going to put this in like mx plus b form. And so I'm going to say plus b. Right? So there's kind of part of the rule. And then I'm going to fill in a point on this line, which I know. So, for example, any of these points, right? There's 2 points that we know on this line. I could plug in the point 14, 6, or I could plug in the point 20, 0. Either one would work. Okay. I'll go ahead and just use 20, 0 because it seems like, I don't know, easier numbers to work with maybe. So plugging that in, 0 equals -6/5 times 20 plus b. And then I'm going to simplify this. So this would be about, let's see, that's going to be 4, and 4 times 6 is going to be 24. And then I'm going to add the 24 to both sides. And so I see that my y-intercept is 24. And so now I can write that part of the function as -6/5 plus 24. Now we can go ahead and write the full piecewise function. The first part of this was 2/3 x. And that happens from 0 to 9. And then I have this 6. And that's going to happen from 9 to 14. And then remember, we've just used 9. We've just included it. So now I cannot include it again. And that goes to 14. I have no problem including that one. But then obviously on the next rule, -6/5 x plus 24, that's going to be from 14 to 20. And there we go. There's our piecewise function for that awesome situation. So that's it for me. I will see you in the next one.